Hello, everyone. Good morning. Thank you for joining us. We're going to get started now. So again, thanks so much. We appreciate your time today. We got about 43 people in today, which is a nice webinar. So again, today we're going to talk about PQ triggers and applications. My name is Ross Signal. I'm the Director of Product Management, Technical Support, and Marketing for Dranitz. I'm joined in the room by Ken DeMario, who is just over my shoulder here. He leads our tech support efforts. I think many of you who certainly are Dranitz owners certainly know Ken very well. So again, just a reminder, please make sure that your audio is muted and keep it muted throughout the webinar. We would appreciate that. If you do have any questions, you can use the chat. And at the end, we will open it up, to use the audio. But again, please be respectful and mute your audio. We would appreciate that. If you do need to contact us at any time, at the bottom, you can see here our technical support email address. We're happy to speak with you, and we'll be referring to that throughout the webinar and hopefully answering your questions throughout the webinar. So again, just to get started here, again, our agenda, my name is Ross. I'm here joined with Ken. We're here today to talk about PQ triggers and applications. This topic is really based upon a lot of feedback from our prior participants in our webinars and also our technical support requests. And, really what's available on PQ triggers, how do I use them, how do I apply them? And that's really what we're going to talk about today. So we're going to look at what are the available methods, certainly focusing on the Dranitz products. Which ones would I use for my particular application? And we're going to talk about several applications today in the CAN presentation, but we're happy to talk about anything else that you'd like to talk about. So again, what are the available PQ triggers? How do they apply to your applications? What are the importance of each? And we'll also touch on which ones are driven by standards, which ones are maybe proprietary or are not driven by standards. And today we're going to cover some major real-world monitoring applications. And the first one is just general power quality troubleshooting. I need to go out and just solve a basic problem, and just how do I generally set up a meter? Nothing really special. To some more specialized applications, such as step load testing, which is important for mission critical, UPS, hospital and healthcare, those types of generator applications. And there's some unique capabilities of the Dranitz products when it comes to that really guarantee your success in that. These are capabilities not available in other products. So we're going to talk about which triggers are important and really how to set up those triggers and how to look at the data in our Dran-View software with this particular application. Similar to inrush testing, we're going to use that same demo file, but what are the unique things needed for inrush testing? It's a very common thing, loads turning on, loads turning off, cold load pickup from a utility would fall underneath that. And also harmonic studies, we're going to focus on that. What do you really need to do for a harmonic study? How would you set up our meters for a harmonic study? And we'll talk about more. And again, for each of these, we're going to speak about the monitoring objectives, which triggers are used, and what are the appropriate settings for each of those applications to at least minimally get what you're interested in. And you can, of course, always add to this. Question just came through. Is a PDH certificate available for this course? Yes. Please email us. You can email me directly, and at the end of the webinar, you'll see my email address, and we'll be happy to produce a PDH certificate for you. As a reminder, like all of our webinars, we're going to be recording. In fact, we are recording today's presentation. We're going to do a little post-processing on it and then throw that up on our website with the library of more than 35 webinars that we presently have posted. Our questions, please chat your questions. At the end, we can open it up for an audio dialogue, but in order to not be disruptive, please just chat up your questions using the chat capability of Zoom. And Ken will be monitoring in the back, and I'll be monitoring as well. And certainly by the end of the webinar, we'll address all of your questions. And as usual, we can't stress more. Please send us any suggestions that you have for future webinars. This particular topic really came from folks like you in suggestions on what's needed in the field, not only for educational purposes, just general education, but how to apply the Dranitz products more productively. So please don't forget to follow us on social media. We have well over 1,000 followers for Dranitz. So please, we focus on Facebook and LinkedIn. So you will see, find our social media channels for Dranitz, Electrotech Concepts, and Gossamer Metrowatt USA. And in fact, these webinars were published on the Dranitz and the Electrotech channels also. Okay, let's begin here and let's get to the point in the topic which we all came for here. Again, we're going to talk about, well, what are the available PQ triggers and the triggering methods that are in the industry. So when you look just general purpose and from a high level, 10,000 foot perspective, the general methods used are generally high and low limits. And usually even from bottom up loggers, we're talking about a high and low limit on maybe monitoring voltage or current. You can even monitor power and different things like that. So simply put, you enter a limit, and when it exceeds the high limit, you get a trigger. When it goes below the low limit, you get a trigger. And it's just logging that. And there's also things called peak limits, and we're going to break these down a little further. But peak limits are, some particular peak has exceeded a limit. So we're not talking about the RMS of a waveform or the RMS over many waveforms, which is what the high and the low limits use for the majority of the time. But peak limits is maybe one sample exceeded a particular limit, maybe such an application for a transient or something. So basically it's a peak implied high limit that is exceeded. Then you have more, let's say, proprietary and specific triggers such as wave shape changes. And these are extremely important, and we'll get to that in a couple of slides. When we're looking actually from a very detailed perspective, you're looking at one AC waveform and you're comparing it to the previous AC waveform. And these are very powerful triggers that are unique and proprietary to Dranets. And we'll give you some diagrams in the next couple of slides to better understand that. So really the bottom line here and a big takeaway when you speak of these general methods, and some of them more specific, but the devil is in the details on how they're implemented and what are the specs of that meter. And what I mean is there are different specifications such as the base sampling rate. And this is the detail of the digitization that you're seeing of the wave shapes. And historically digitization, years ago was 32 samples per cycle. Again, these are usually represented in samples per cycle, digitized samples per cycle. Then they went to 64, 128, 256. And really the common sampling rate right now is 512 samples per cycle on basic power quality meters. And probably basic is the wrong term to use, but that's the base sampling rate that is used. Some offer high-speed transient sampling and things like the Dranet's HDPQ Explorer and products like that. So leading on to that, you have transient sampling rates, which is much higher, and transients are basically a momentary but fairly high speed excursion from your waveform, and we'll show you pictures of that. And you need higher digitization for that. And so again, if applicable, usually that's referred to in kilohertz or more appropriately megahertz in today's world. Like as an example, the specifications for the Dranet's HDPQ Explorer is in megahertz for its high-speed transients. So today we have a lot of standards available to us. So a big question and part of the devil in details are, what is the compliance with the available standards? And you start out with the most common types of events, sags and dips, which are under voltage. Sag is a term used here in the United States, which is defined by the IEEE. DIP is more of an international term, which is defined by the IEC. It's see some of our other webinars to get the differentiation here and more details on these standards that we're going to be referring to. So you have the sags, the dips, the swells, which is an increase in voltage. An interruption would be no voltage at all. Frequency measurements, harmonics, and more, they are defined by IEC 61000-4-30, which is presently in its 3rd edition with the 4th edition pending maybe sometime later this year. We're not sure. Harmonics, again, a base harmonic standard out there is IEC 61000-4-7, which is part of the IEEE 519 that's commonly used in the United States. And it's starting in its 2014 edition. And also it is referenced in this IEC 61000-4-30 as well. So this is the base standard used for harmonics. We'll elaborate on that when we get to some harmonics information here. You have a newer term called supraharmonics, and supraharmonics are harmonics in the frequency range of 9 kilohertz to 150 kilohertz. To give you an example, the 61000-4-7 caps out at about 3 kilohertz is this standard range we've been using forever or for the use of harmonics. And that's about the 50th harmonic. Superharmonics is kind of a band that's much higher in frequency. It's going to become part of the next version, edition 4 of 61000-4-30, but it will be in the informative section, which means it's not required. It's just information to be provided. But there's going to be techniques in there on how to do these newer types of superharmonic measurements. And that's kind of the delay in the standard right now. They're evaluating various types of techniques to implement a technique that's practical to implement by manufacturers such as Dran-View. So then we go into higher speed events potentially, such as transients. Again, transients are a change in the wave shape. Most people consider transients a positive kind of peak thing, but there's negative transients as well that take away energy from the waveform. And that goes to what you can trigger and how you can appropriately trigger this. And we'll talk about that. So transients, there really are no standards on transients. Transients are referenced in standards such as -4-30 in the informative, again, not required section. But no techniques are given on how to measure them. So it's kind of the Wild West when it comes to standards for transients. Manufacturers generally just develop their own techniques, such as what Dran-View has done. And really, it's just higher speed sampling to capture them. But again, those are for peak transients. Wave shape change triggers, which are very important. There's no standards for those, and proprietary methods, and there's several in the Dran-View products, are for applications for negative transients or intermittent noise on an AC cycle or on a power line. And think of a power factor correction capacitor switching in. That is a negative going transient. So if I have a peak transient trigger, I'm not going to capture that. I need something to capture a negative transient and or a wave shape trigger. And that's where the power of these truly come in. And we'll talk about that. Well, then you have the resolution of the measurement. All right. So when we're talking about a sag, a dip, blah, 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 well, what's the resolution? Okay. And how do I measure that? And that's defined primarily in our industry by IEC 61000-4-30. But there's different resolution for different types of parameters. So as an example, a dip or a sag, which we call an RMS change, well, that's driven by a half cycle increment of a 1 cycle window. And again, we're going to get into this. Others are 200 milliseconds, others are longer. So we're going to talk about this in the coming slides, and we're going to look at, well, what's the trigger type and what's the importance of it? What's the resolution and how is it measured? And more appropriately, how do you set it up in a meter? So that's what we're going to get to. Okay, and really continuing along, just starting with that, we have our first type, which we call here at Dran, it's RMS variations. It's really just referred to in the field as those sags or dips. Again, a sag is an undervoltage, a dip is the same thing, just an IEC term. You have a swell, which is an increase in voltage, and an interruption where voltage is not there at all. All right. So these are voltage variations. These are also current variations as well. The same triggers are used except for interruption, but there's no names. There's no current sag. There's no current swell. So when you see these names, sags, dips, swells, interruptions, these are implied to be applying to the voltage only, but current is measured in the exact same way if your meter is compliant with at least edition 3 of 61000-4-30. That's when they introduced measuring current really in the same way that voltage is measured. Excuse me. And that goes to that resolution that we're going to talk about in a few minutes. So what are the applicable standards? Again, 61000-4-30 and IEEE 1159. 1159 defines the names here. 61000-4-30 defines the techniques and the windowing and all the stuff on the right here, which I'm going to explain in just a minute. All right. You have the limits. Well, limits are typically high limits, low limits, and interruption limits. And really a high limit, as its name implies, that's a swell limit. So the voltage, and the same thing for current, although you won't call it a swell, drifts above that limit. Let's call it 132 volts. Now it's 135 volts. I've created a swell limit or a high limit. Same thing for a low limit. The interruption is usually it's considered a very low limit, and it's just usually a percentage of that nominal voltage. And usually it's about 10% of that nominal voltage. So, on a 120 volt system, that may be 12 volts or something like that. And really interruption means that there's just no voltage at all. So if it falls below that level, consider it, an outage at that point using a different terms. Okay. So a point here in the United States is that 1159 defines names, i.e. sag, durations, and suggested limits. Durations, it's measuring how long it's been out of limits. and the limits and the minimum, maximum while it's out of limits. But 1159 does not define the standards, or I'm sorry, the measurement methods. Those are defined, and what's implied to be used around the world, including in the United States, is 61,000-4-30. All right. So the resolution and the measurements, again, per 61,000-4-30, and this has remained basically unchanged since its first edition back in 2003, 4, 5, something like that. You're looking at the resolution of one AC cycle, but you're stepping in what's called half cycle increments. So if I turn on my little drawing tool here, hopefully this works. I'm still evaluating. Of course, it didn't. Let's try it one more time. I got to choose my box here. Basically, we're evaluating something that's one cycle in duration, and you can see this. But what the meter is doing, it's actually incrementing by a half a cycle to be compliant with 61,000-4-30. So my next cycle is going to be this, okay? I'm sorry, I'm getting a call here on Teams. So, and the cycle after that will be this, will be another half cycle increment. So you can see here we're measuring, or the meter is measuring one cycle at a time, but incremented at half cycle increments. So hopefully the way I drew it out is clear here. And that's URMS 1/2 is the technical term for that. So really the resolution of any high or low limit, a sag or a dip or an interruption limit, is one cycle, but that incrementing period is not one cycle, it's 1/2 of a cycle. So the point being, you have overlapping measurements here. You can see this area overlaps with the cycle, before and after it, and the same thing over here. All right, hopefully that's clear. So that's the way that particular type of trigger works. Okay, so then we continue on. If I can get this thing to advance, and now it's not working, just bear with me a second. All right, it appears that may have locked up here. Just bear with me. Oh, you know what? I bet you have to turn off the drawing tool and go back to the mouse. Okay, there you go. I apologize. Let me just clear this, clear all drawings, and we should be go. Okay. And so how do you set these things up? This example is with our Dranitz HDPQ line, and basically you can see it's a high limit for a swell limit, a low limit for a sag or a dip, and an interruption limit. Now we do have automatic setups in these meters, so what we call the wizard or the manual setups automatically go to those same limits in the automatic setup. And the way the IEEE 1159 defines these kind of rules of thumb for the industry is plus or minus 10% of what the nominal is. And the nominal here is 120 volts, which is our line outlet in the United States. And basically 10% high is 132 volts, 10% low is 108 volts. And that very low or interruption limit is 10% of that nominal, which is 12 volts. So the meter will set itself up automatically for these limits. And you just simply click, and this is a PowerPoint, I can't do this. You just simply click on a cell and you open it up and you can make it tighter. You can make it any raw voltage or current that you'd like, or you can click this button over here and which says set as percent of nominal. So if you click that, now you're talking in percents. So if I click this right now, this would say 110%, 90%, and 10% would be it. So again, you can switch back and forth between that and the real magnitude of the voltage or the current. I can say click this and go to phase current A, and now I'll be changing the current. That's the current triggers. Very similar method, but you're looking at high-low limits on current. Just as a quick side note, we do not recommend that you turn on current limits unless you have a very specific application. And the reason being is that the current's always fluctuating, something small to something large, and as your power system goes through its dynamics, and it's going to create a lot of triggers. So you need to know really what your loads are and what your application is. They work perfectly fine, but again, be careful what you wish for when it comes to that, because you may get a lot of triggers that you may not expect. So continuing along, you have something called the magnitude of supply window, and the applicable standards, again, driven by 61,000-4-7, which is incorporated into 61,000-4-30 and IEEE 519, which is harmonics here. This is really a 12 or 10 cycle window that is used for evaluations. And universally, it's a 200 millisecond window. And this is 12 cycles at 60 hertz and 10 cycles at 50 hertz. And this is the basis for the harmonic measurements used by, again, 61,000-4-7, which is part of -4-30, or the IEEE 519. So we're not looking at one cycle, we're looking at 200 milliseconds worth of information, which is brought up again, 12 cycles at 60 hertz and 10 cycles at 50 hertz. So again, primarily used for harmonics, although they're used for other parameters. So you'll see VTHD, ITHD, individual harmonics, interharmonics. This is the basis for those measurements of compliant meters, let's say, again, the 200 millisecond window. So the limits that are applied, usually there are high limits or low limits. Most of the time in the common way is a high limit. Most time people aren't interested in how low their harmonics are. It's usually how high they are and going past certain limits. So again, that resolution is 200 milliseconds, that 10, 12 cycles that we spoke about. And this is non-overlapping and gapless. And what that means is that when I get to my next 200 millisecond window, there's no break time in between. So I'm looking at one 200 millisecond window, and then without gap, the next 200 millisecond window, and then the next, and throughout infinity or long the monitor is turned on. Now that information is aggregated into 1 second, 3 second, and 10-minute intervals for various other types of things. And you may find them for, short duration, very short duration, or short time harmonics in 519, and other standards like that. So they are aggregated up within the meter as per these standards and what they require. So these are things that are driven by standards, not driven by manufacturers. So the manufacturer is compliant, and then the standard defines what they do. They're not compliant, who knows what they do? It may be right, it may not be right, but they're certainly not in compliance with the standards. So just as a note, again, as we do here at Dranitz, this 200 millisecond windows, or these windows, may also be used for watts, VA, VARs, power factor, things like that, and the basis for energy and demand. All right, so you can use this for other tasks as well. Excuse me. So we have something called supraharmonics that we touched on before. Again, this is in the range for 9 kilohertz to 150 kilohertz. And they require, just as a note, higher order sampling, because again, we're going well past the power band here to get up to 150 kilohertz. Really, power meters, there's no standards today to do this. Again, I mentioned edition 4 of IEC 61000-4-30 will have that in the informative section, but that's months away or maybe even longer away. Depends upon the duration to evaluate those methods. So they do require higher sampling and special measurements than typical PQ meters, but if you have a meter, certainly like the Dranitz HDPQ, it samples and digitizes at 512 samples per cycle. If you do the math, that takes you out to 255th harmonic. Bear in mind that these standards over here, with the exception of superharmonics, goes to the 50th harmonic. So you can see this is a much wider frequency range than is required, but it does overlap. When you look, this is about 15.5 kilohertz at 60 hertz. So that is within this range. It's a lower end of the supraharmonic range. And our Dran-View 7 software can pull that information out. You can't see that on the meters directly because they're based upon these standards, so they'll only give you to the 50th harmonic. But the harmonic and time plot calculator of Dran-View, a standard capability of Dran-View 7 Enterprise, can do that for you. And it's an example of doing that is the G55 standard in the UK, which required to go up to the 100th harmonic. They doubled it in the newer G55 standard that they released over the last few years. So the solution for our customers was to use the Dran-View 7 Enterprise to pull that information that their meters already had that they've been using for years. So how do you set up anything that's based upon the magnitude of supply? And typically that's THD, VTHD, ITHD. Well, usually that's just a high limit. And, you can ignore the very high limit here. So the Dranitz meters for these types of what we call journal events have high and low limits and very high and very low limits. So consider this kind of a yellow area if you're going to use all 4 of them. And so if it goes high, it's kind of a warning. If it goes very high, consider it, a serious problem, and the same thing for maybe very low. Most of our customers typically use just the high and the low limits just to simplify it, but you have these additional capabilities if they are there. And again, this is a snip directly from the setups of an HDPQ family product. Excuse me. So then we get into frequency. So what's the available standard? And it's interesting, there are very few standards for frequency, and probably because frequency is applied differently depending upon your application and the types of loads that you're testing. And you'll understand that and see what I mean in a minute. But the direct one that Dranitz follows, and any meter that's compliant with 61000-4-30 is driven by this. Again, what's it used for? Frequency. Parameters F, that's the obvious part. The limits are typically high and a low limit. So I'm supposed to be 60 hertz in the United States. I have a limit on the high, 60 point something, and a limit low, 59 point something, 58 point something, and you're kind of tracking that. So 61000-4-30, well, that defines a 10-second interval. So that's really okay for just general power lines and stuff, but there's applications that require cycle by cycle frequency or something a little finer than that. So that's the important thing, because this 10-second interval, that's a number of integer cycles over 10 seconds divided by the duration in cycles. So that's basically an average over 10 seconds. When you're looking at a generator startup or a cold load pickup or a UPS transfer, well, you're interested in, well, how does the system react to that? Because you're providing power and frequency for that system. The utility is not doing that. It may not be as stable. So those applications typically require what's called cycle by cycle frequency. So when you're looking at every AC cycle recorded, and what is the frequency of that one? And what's the frequency of the next one? Well, standard power meters typically can't do that, probably because they're driven by these standards. However, Dran-View 7 can compute the cycle by cycle frequency using any waveform recorded by the HDPQ and other Dranitz legacy meters. So if I get a whole slew of wave shapes, I don't know, 50 cycles or something, Dran-View 7 Enterprise, using the harmonics and time plot calculator, can compute and plot for you the individual frequency of each cycle and get maybe a plot like this. So this is during a generator test or a step load test. When a load switched in or switched off, this is how the frequency drifted up. Okay, you can see from around 60 hertz to about 61.5 hertz. Using this 10-second interval, rather, you could not do that. So these are specialized capabilities, extracting more information out of the basic information available in an HDPQ or PX5 or older products, and using it for these particular types of applications. So extremely powerful. Doesn't seem that way at first look, but it makes these instruments capable, very capable of these applications, where other instruments you'd have to struggle to not only trigger the information, but also get this type of information out of it, the results. So how do you do frequency settings? Again, the triggers, again, just high-low. There's no settings other than maybe the base frequency that the instrument's going to measure, 50 hertz versus 60 hertz. But again, a frequency trigger on the meter itself is just a high-low limit. Using that information within Dran-View, well, that's a different story on the harmonic and time plot calculator, which we'll give a quick overview of in a few minutes. Well, now we talk about peak kind of measurements. And think of this over here. This is a little scribe of a transient here, and this horizontal line would be the limit. So you're looking for one sample to go above that limit. So we're not measuring the overall RMS of these wave shapes, as we spoke about before. We're looking for a peak that happens, something switched on or off, or in a bad case, a lightning strike or something like that. So more importantly, this is a positive peak, and positive peak does not have to go in the positive half of the waveform. That can also go in the negative half of the waveform. Consider it adding energy to the waveform. So what are these peak triggers for? Well, what are the applicable standards? There are none out there. So it's every manufacturer's on their own on how they implement it. So you really should go look at the details to make sure it's appropriate for your particular application. So these are for positive transients only. Again, it could be on the negative half of the waveform. It can't detect negative transients. As an example, this is a power factor correction capacitor switching in, which is inherently a negative transient. So the voltage doesn't go up, it goes down. So this type of trigger will not detect that. That's where the wave shape triggers come in from Dranitz. All right. So what are the limits? Well, they're high limits, such as peak limits. Now the details is sampling rate dependent. So if this is a high speed sample, well, that's good. If it's 128 samples per cycle, well, that's not as good as 256, which is not as good as 512. So to just do some math for you, the digitization at 512 samples per cycle, which is the HDPQ, the resolution is 32 microseconds. And that's the distance in time between two successive samples on there. And that's 39 microseconds on 50 hertz, because it samples just a little bit slower. All right. So some meters, again, also have high-speed peak transients, such as the Dranitz HDPQ Explorer. The setups are very similar, but, again, the resolution is much higher. And you can see here's the settings in the HDPQ Plus for the peak transients. Again, you're just looking to get a setting that exceeds the value of this peak here, kind of as marked by this horizontal blue line here. So that's the method here. Okay. So wave shape change triggers. This is extremely powerful, and this is what I'm referring to before. What are the applicable standards? There are none for wave shape changes. There's something proprietary to Dranitz, in which we actually have two different algorithms. What are they for? It's for any change from cycle to cycle. So in general, what these do, these look at one cycle and then compare it to the previous cycle. Dranitz has two different ways to do that. And you're looking for the difference in that. And that can be a positive, or more appropriately, a negative transient, or more powerfully, I should say, a negative transient for voltage and current. So I'm comparing my present cycle to my previous cycle, and there's some sort of change that I want to trigger on. Think of that power factor correction capacitor switching in, like this image right here. These are nice sine waves until this happens. All right. And then it goes away within a cycle. So the wave shape change triggers on that. And that's very similar for the transient or the system load testing, the step testing that we're going to talk about in a little bit. So what are the limits? They're method specific. Again, we might as well describe it now. Dranitz has two methods, and this is mostly due to the history of our product line. Not that anyone is extremely more powerful than the other. There are customers still have preferences which one they use. So this is the RMS difference or deviation. So you have my present cycle, and I subtract my previous cycle from it. Literally, you line them up and you do a subtraction sample by sample. And you're triggering on that little difference, that RMS difference. So if they're exactly the same, this will be 0. And the difference is what the difference is between those cycles. Then we have a slightly more complicated triggering method called the wave shape difference. And really what this does, it looks at a particular window of the waveform and compares it to that same window in time of the previous waveform. So it divides this into a percentage of the waveform, maybe 10%, and you'll have 10 of these little windows comparing to the previous waveform, and you're looking at that difference, right? So the resolution is based upon your sampling rate. It detects a change in the present cycle to the previous cycle. Extremely powerful for those generators and step load tests and power factor correction capabilities. And really the unique capability is triggering on negative transients and incremental changes in voltage and current. So these are things that are not going to change the RMS of the wave shape. It's not things that are going to really be peak detected, because we have other methods for that. These are things that are subtle changes, but also negative going changes. They could be abrupt, but again, it doesn't change the RMS, and it can't be measured with a peak. So these wave shape changes are extremely powerful when it comes to that. And you can see some pictures here on how we capture it. So this is VNI variations that don't exceed. So you had a reduction in voltage here, but it didn't exceed the high and low limits that you set. This happens to be current, but it could be the same for voltage. It really doesn't make a difference. So it didn't exceed your high or low limit for RMS, for voltage, a dip or a swell or something like that, or capture those abrupt changes like we talked about for our power factor correction capacitor. How do you set up the meters? Again, a little bit different. We have two available methods, the wave shape difference, which again, as I described before, you're comparing a window of the present cycle, and here's a depiction of that window, to that same window of the previous cycle, that same point in time. And the user sets the window size, the size of this window, and that's that duration, and the trigger limit. Well, that's the threshold, okay? So it's very similar to this method, which is subtracts the entire cycle, and you look at the difference, except this is just dividing that cycle into various windows. So if I set the duration to 100%, it's basically the same algorithm, because I'm evaluating that entire wave shape. A little bit complicated, but once you understand it, it's fairly basic in how to do it, okay? So let's get into the details over here. Now I'm going to be switching back and forth. Let's talk about the specific applications. Then I'm going to switch over to Dran-View 7, and we'll show you some examples of data captured for that particular application. And then you can chat up any questions that we have. I think we're doing okay on time to cover your direct questions. So when we look at general power quality troubleshooting, now that can mean different things to different people and different applications, but what are the applications here? Well, it's general purpose. It can be anything. Excuse me. So it can be a facility monitoring, utility, industrial, residential, retail, whatever it may be. So I'm just looking to reactively solve a power quality problem. Usually it's reactive, meaning something's failed. You're hoping it happens again when you have a PQ meter, an HDPQ as an example, attached to that line. So you're troubleshooting reported problems, maybe voltage variations due to, breaker tripping, loading, harmonics, whatever the deal is. So you're looking for that. The key triggers involved, well, this could really be anything, and it really depends upon what that problem is. But basically, you are setting it up for voltage and current RMS. So sag, swells, transients, and possibly changes in RMS. Usually people aren't triggering on that, but the journal and the periodic limits that are given by the meter is more than enough to look at that. You can get the minimums and the maximums. And again, triggering on RMS current is very challenging due to the fact your loads are varying all over the place, and you got to get those limits right. And it certainly work fine, but you get many triggers a lot of times if you're not set up properly. And you can have other triggers and peak transients. You're looking for transient issues, switching, contactor issues, lightning, things like that. And also THD would be important if you're looking for harmonic compliance. So the challenges are, well, you want to make sure that your random PQ problems, that, the challenge is maybe they don't coincide with your PQ survey. So you set it up for a week and your problem didn't happen. If you have very random problems, maybe you have to monitor for a longer period of time. Or if you're lucky, it happens regularly and you capture it immediately. Or it may not be a power problem. That's another thing to consider. So the problem occurred, you put your power meter on there, but it didn't trigger on anything. So assuming that the problem was within the, exceeded the trigger limits, and with our products, usually it does if set up properly, it may be another issue, maybe a mechanical problem with something, or a software rebooting, or a hardware problem with a power supply or a server. So what are your CT considerations? Well, as in most applications, you need to make sure your CTs are properly sized for the varying system load. So you have to look at your minimum current being measured, your maximum current being measured, and the typical, and make sure that your CT is within that range. So example, if you have a 500 amp, just one of our TR2500s, and when you turn on your loads, you get 2000 amps. Well, that's probably not a good application for that CT. You need something with a higher range that can capture that, because you're going to saturate that CT. So again, just one sort of random example. If you're looking at harmonics or current transients, make sure these CTs have the bandwidth to capture what you're referring to. As an example, clamp CTs and anything permanently installed usually have a bandwidth less than a kilohertz. Usually it's only 400 or 500 hertz. So which is fine for RMS measurements, not a big deal. But if you're looking for, let's say, a medium to higher order harmonics or current transients, well, your CT is not going to pass that for you. A better solution, if at all applicable, is one of our flex CTs, which has a much wider bandwidth and is very appropriate for harmonic and current transient measurements. The analysis, again, your objective here is to compare the results to your system specifications, and really, did the power quality event coincide with the reported problem, and how to manage that. So let's switch over to Dran-View here, and I'm going to probably have to change screens. Okay, so here's an example of Dran-View. And you can see that I have a basic test here that we've done. This is something that we do for our evaluations within our engineering lab. And this is not unlike what you do for a very basic and a very short-term power quality survey. Again, general purpose power quality survey. And what you have here, this is a timeline of what the measurements were. Again, this is something a little short. You have the wave shapes recorded on the right. And you can see I've honed this down to a single phase measurement, and you can see the voltage goes down and the current goes up. And that's what I'm looking for here. I'm looking for what is the impact on that. And I obviously had something turned on. And if I had my power quality problem at around that same time, basically that would maybe trigger a breaker or have a power supply reboot. And this is the information that you would get from that. And, something interesting here, you can see this was taken from our HDPQ Plus Guide or Explorer, which has got the answer module, the sag directivity answer module. So for a sag or a dip that was downstream, it will tell you that, which means it was downstream from the monitoring point. And if I switch to another one here, here's an instantaneous sag. You can see both the voltage and current go down at the same time. And this is upstream from the monitoring point. So just some of the throwing in some just the basic rules of how directivity decisions work. Okay, so next one is the step load testing. And we've done sections of webinars on this. And really, this is extremely important for applications such as generator testing, mission critical testing and applications like that, and really in hospital, healthcare, internet applications, cell phones, things like that, or cellular data centers, things like that. And it's very common that they're basically inducing loads and they're stepping loads into the system that represent 0 to 100% of the capacity of the system. And what they're looking for when they step these loads in, what is the reaction on the voltage, the frequency, and maybe some other parameters that are of importance to them. So you can see this particular test goes from 0 to 25%, then 25 to 50, 50 to 75, and 75 to 100% of what the capacity is. And then it steps down in those same increments. And then they do 0 to 50, 0 to 0 to 25, 0 to 50%, 0 to 75%, and a couple at 0 to 100%. So, excuse me, they are looking at, well, how does the system react to switching all that and making sure that it's within the manufacturer's limits of the products and the specified design limits of the facility. So there's a couple of concerns or challenges with doing this. And really, it's capturing the information that's required. And when I think about this, if I'm triggering on current, if I just have a current high limit, where do I put it? Okay. And how do I know it's going to trigger and how am I going to stop my triggering? So what's extremely powerful here, not only the voltage and the current trigger limits that you can have, but the wave shape change limits. So when you look at the wave shapes here, which we'll see when we switch our slides, you'll see that there's an abrupt change in the wave shape. Well, what's powerful for that? Those waveform triggers, the RMS difference or the RMS deviation, either one of those will work because we are changing when that current switches in, you're abruptly changing the waveform. And that's a baseline trigger used by most of our customers for these particular types of applications, okay? So again, the challenge is triggering on those current setups or current steps, and the wave shape triggers are very, very beneficial versus the higher low limits, which is kind of a moving target for this. Excuse me. So the CT considerations really, I mean, the same as anything else for this. Does it measure this entire range? So can I measure, down in, the 25% and all the way up to 100% of what my load is with a little bit of headroom, because you can see there's some overshoot here. So you want to be able to capture this. And usually you can capture, certainly with the Flex CTs, a short duration. There's a very high crest factor, a reasonable crest factor on that. So, you have to be considerate of your RMS limit high and make sure that your overshoots and your transient currents will be able to be measured by that CT. So what's the analysis here? Well, you're looking for the testers here, the troubleshooters, the commissioners, whatever they're doing here, looking for the reaction of the system to the step load changes. And what's the effect on voltage and the RMS and the transients, frequency and other. So you're looking for the step in current. What did the voltage do? What did the frequency do? Which is easily seen if I switch over back to Dran-View. And I'm going to switch over to my step load testing window that I have. Okay, so you can see here's that step load. I think this is the exact same test that I had shown on the PowerPoint slide. And you can see here's the step test. Here's the current that we're seeing. And I honed into the AB voltage and the A current just to make things simpler here, but you'll see similar results on B and C. And you can see I stepped to 25. Well, I didn't. Our customer stepped to 25%. And here is the change in voltage, 50%, 75%, 100%. And the same thing when they step down. So you can see there's a little voltage dip when it came, but you can see it did not exceed the dip limits or the sag limits or the swell limits here until you get to these impulse tests. And probably when you get to the 50% test and the 75 and the 100% test, you can see it goes out of their voltage limits here. So you can see the changes in what's going on. And when you actually look at the wave shapes, you can see over here where I look at this is a wave shape trigger. You can tell it's channel AI, which is current RMS deviation trigger. That is the trigger that triggered in this particular application. Again, RMS limits did not kick in. So I would not get an RMS trigger for voltage, certainly, this early in their test. So you can see what happened over here. Look at the wave shapes recorded by the meter. You can see the current basically goes from nothing and all the way you see it peaks up to, I don't know, about 2,500 amps, maybe a little bit less than that. And you can see how it decays down to its more steady state value, and it's still going here with that particular trigger. And you can see we have some retriggering here, and we look a little bit later on in the test. So again, they're looking for that impulse. So as an example, if I go here later, and if you click these little upside down triangles, I can randomly go to different parts of the test here. Now I'm looking in, you can see we're turning on and we're going, when I look over here, we're going to 100% of the load. And you can see this is the change. Look at the peak current now. If I look at that, I let my cursor go. When I'm about 7,700 amps, I'm looking at over here. So you can see how high that overshoot went. And you can see it starts to come down within the nominal to where it's going to settle after that test. And again, that's the big thing that they're looking for. Where did it peak and how does it collapse down? And what's the reaction to that impulse? They call it transient testing, but it's not really transient in the terms that we use things. All right. Another important thing is looking at the frequency. So if I change my plot over here, and I go look at the frequency, I look over here, and what's the frequency of that impulse? So this is that cycle by cycle frequency that I was talking about. And we use the harmonic and time plot calculator. I'm not going to run it here, but I'm going to go to the data and then the harmonic and time plot tab. And you can see frequency over here. So when I run this, I'm not going to do this again because I've already done it. It basically takes any wave shape in the database and computes the frequency of that wave shape. So all these squiggly lines for voltage and current, you can see I'm looking at the frequency over here of the voltage, I think is what it's measuring. All right. So you can see how the frequency changed from 65 all the way up to 70 something hertz during that particular that particular test. So you can see how things changed over time. Really powerful, extremely powerful, driven by the wave shape change triggers. Our next type of test is the inrush testing. Again, cold load pickup, motors starting, transformers energizing, different things like that. Where are the applications? Well, they can be all over the place. Facilities, again, for motors and transformers, and that would apply to industrial and other applications. Utilities would have those, but maybe at a cold load pickup where they have an interruption or an outage, or they're bringing up a substation or a distribution system. It's a very similar thing. You go from basically no current or little current to a lot of current. Now, when you think about that, that overlaps with the step load testing that we just gave before, but a different sort of measurement. So the objective, you're looking at motors, transformers, and other testing and things like that. And you're looking for the impact on the system. All right, the key triggers, voltage, current. Again, these wave shape triggers. For this type of application, you can just do a current high limit. And you just got to know what it is from your nominal steady state, and basically you trigger on that high. But a lot of people use the wave shape triggers, very similar to what we talked about in the step load test from before. So again, the challenge triggering on that inrush current and being able to capture that peak inrush. And that's where the selection of CTs comes in, because you need to measure, well, its peak and overshoot, but also its steady state when that happens, right? So that's challenging without saturating those CTs. And so you have to make sure your current probes are up to snuff. And usually flex CTs are the best choice for that. So what the troubleshooter or the operator is looking for, what are the effects on the voltage, the load capacity, breaker trips, things like that. Using the bookmark or the snapshot feature, I created a snapshot which basically captures that. And that's really what I put in the PowerPoint. And again, this is buried in that step load test file that we have. And this would be an example of an inrush test that you would want to be looking at. And again, you can look at the individual events here. You can see what triggered, and this is, I'm already zoomed into what the effect on the voltage was and the current. So you can see our current goes from basically 0 or just a couple amps all the way down to 4,000, or actually peaked over here at, what was it, 7,000? About 7,000 amps, and look at how the voltage dipped at that particular period of time. So basically when this turned on, this would have created a sag or a dip event during that. And some loads may have been affected by that. Okay. So it looks like, yeah, I had the comment, looked like I checked power factor. Maybe I did by accident before. So let me go back and I will correct that for you folks. So thank you for the chat, whoever, Kevin, who sent that up. So let's go. And again, going back to what we were looking at before, I will go over here. And I was, Kevin, when I looked at it and I saw a percentage of unit PU, I knew that something wasn't right. So let's go over here. You're right. I probably did check power factor. And there you go. You can see the impact of the frequency. So thank you for correcting me on that. So you can see it went to a little below 60 hertz. You see how it drifts down, okay, when this particular voltage goes up. So anyone that I select, I can go down and look at them. You could see what the cycle by cycle frequency is. So you can see the load turns off here, and you can see how my frequency drifts up at the output of that generator, that UPS, whatever they were looking at. Okay, thank you again for correcting me before. But again, the motor inrush application, or the inrush or the cold load pickup, is very similar, but you're really looking for just that firing over here, like I showed you in the snapshots, okay? That energization going from 0 to whatever it's going to max out and peak when it turns on. All right, so it's a very similar, but a little more specific and honed down application. So when we talk about that harmonic testing, it's complicated statistically in what you do and how you do it, but the setup of the instruments, at least the HDPQ family, is really basic. So what you're looking at, you are looking at the a facility, a utility, whatever it may be that's appropriate for you. Industrial, DER, distributed energy resource applications, maybe a solar farm or something. So the objective is, well, you're evaluating the system harmonics. In the United States, that's for compliance with IEEE 519, usually version 2014 or higher, and also maybe to IEEE 1547, which is an IEEE standard looking at the interconnect of DER systems, solar farms, wind farms, et cetera, to the grid. Okay, and they call this standard, this 1547, calls out other things. Or maybe you're just troubleshooting. You got a harmonic problem. You think something is tripping off, so you're just looking for just basic VTHD. The key triggers: THD, ITHD, individual harmonics, and the statistical evaluation by IEEE 519 2014, okay, and higher. And what that is, there's a whole statistical evaluation that's done in 519 using that IEC 61000-4-7 that I referred to in the beginning of our webinar. And basically it breaks things down into short time and very short time harmonics, things like that. And it's looking at compliance and a statistical analysis, which is defined in the standards. And basically what you get daily compliance reports and weekly compliance reports. All right, the daily compliance reports is based upon very short time harmonics. The weekly compliance report are based upon short time harmonics. Each day you'll get a pass fail report, and you'll see what information is provided. You'll know, as here, though, the THD failed as an example, and what individual harmonics were out of compliance limits. So 519 defines what these limits are, but they also define what the measurement techniques that are there to do it. So what are the challenges? Again, getting the proper measurements. Super harmonics are not a part of this. They are not defined in the standard. In fact, they're not defined in any current release standard. Again, that's a future concern. What are the CT considerations? Well, make sure your CTs can pass up to the 50th harmonic. Most metering CTs usually clip at like 400 hertz, 500 hertz, as well as even the TR clamps that we sell. The flex CTs that we offer are probably a better solution for these types of applications. And the harmonic compliance reports. The Dran-View HDPQ family gives you these compliance reports and basically shows you in black and white how to look at this and what the results are. You'll see this on the meter. And I'm going to just switch over, and let me switch to this particular session. And we don't have any snapshots. So we'll look here. And if I look down, if I scroll down, you will see here are my individual compliance reports based upon this standard. So you will see the pass fail. And this happens to be a test that we did in our lab. This is not a real customer for this particular report, but you can see the THD failed. And these are the individual harmonics in red that were out of the limits. Again, these limits are applied or defined by IEEE 519 2014 in this particular case for both voltage and current. And it's based upon the nominal voltage and the short circuit current, the available current in the circuit is what's used for that.